September 20th, 1942. Naval Air Station North Island, San Diego, California. Lieutenant Commander Eddie Sanders gripped the yoke of an aircraft that shouldn't have been in American possession. His hands slick with sweat despite the crisp morning breeze drifting off the Pacific. The instrument panel before him bore Japanese markings. The controls felt alien. The entire cockpit reeked of oil and unfamiliar metals. Beyond the windshield, armed sentries patrolled the hangar, their orders strict since the precious cargo had arrived 3 weeks prior. This was the world's most prized airplane, and Sanders was about to become the first American to pilot it. He released the brakes, and the Mitsubishi A6M model 2110 fighter rolled forward, its engine humming with surprising smoothness. In mere minutes, this single test flight would reveal vulnerabilities that would reshape American fighter tactics and shatter Japan's dominance in the sky. The secrets hidden within this captured aircraft would help forge a weapon that would down more than 5,000 enemy planes and shift the momentum of the Pacific War. The process had begun not with this flight, but 5 months earlier on a rain-soaked island in the Aleutians, where a young Japanese pilot made his final landing, June 4th, 1942. On that same day, 300 meters to the east, American dive bombers obliterated 4 Japanese aircraft carriers at the Battle of Midway, permanently altering the Pacific conflict. Yet in the Alaskan Aleutians, a smaller yet equally consequential drama was unfolding. 19-year-old Flight Petty Officer First Class Tadayoshi Koga launched his Zero fighter from the carrier Ryujo as part of a diversionary attack on the American base at Dutch Harbor. The morning mission initially proceeded smoothly. Koga and his wingmen, Chief Petty Officer Makoto Endo and Petty Officer Tugo Shikard, struck Dutch Harbor with devastating accuracy, shooting down an American PBY Catalina patrol bomber and strafing survivors in the water. The Zero performed flawlessly, faster and more agile than any American plane in service. Then a single bullet changed everything. Ground fire from Dutch Harbor, likely from a .50 caliber machine gun, hit Koga's aircraft, severing the oil return line. In an engine reliant on precise lubrication, this was a fatal blow. Oil began spraying from the damaged line, and Koga realized he had perhaps 15 minutes before the engine seized completely. He radioed his flight commander about the damage and turned toward Aleutian Island, 25 miles east of Dutch Harbor, designated by Japanese planners as an emergency landing site. A submarine waited offshore to rescue downed pilots. As Koga neared Aleutian Island, he spotted what appeared to be an ideal emergency landing strip, a long stretch of flat grassland half a mile inland from Broad Bay. His wingman circled above as Koga made his approach, landing gear extended for what should have been a routine wheels-down landing. Shikard, flying overhead, suddenly noticed glistening water between the grass on his second pass. Horror struck. The field was actually a bog, the grass concealing knee-deep mud and standing water. He tried to radio a warning, but it was too late. Koga was already committed. The Zero's wheels touched the grass at roughly 80 km/h. For a fleeting moment, the landing seemed successful. Then the main gear sank into the soft mud beneath the vegetation with tremendous force. Physics took command. The lightweight fighter, its tail still moving at landing speed, flipped violently over in a cartwheel, slamming upside down into the bog. The impact snapped Koga's neck instantly. His body remained suspended by the seatbelt in the inverted cockpit, his service pistol and samurai sword still fastened to his waist. His flight suit unblemished except for the precise medical taping from prior injuries. Above, Koga's wingman faced an agonizing choice. Standing orders demanded the destruction of any disabled Zero to prevent enemy capture. They circled the crash site repeatedly, guns ready, scanning for signs that their comrade survived. The aircraft lay so intact, resting upside down like a turtle, they could not bring themselves to fire. Perhaps Koga was alive, trapped and waiting for rescue. After multiple passes, with fuel dwindling, they reluctantly returned to the Ryujo. The submarine assigned to rescue downed pilots scoured the waters near Akutan for hours before being driven off by the American destroyer USS Williamson. Koga's body and his Zero remained alone in the Aleutian wilderness, 5,000 miles from Japan, destined to reveal every secret of the Empire's most feared fighter. For 5 weeks, Koga's Zero sat undisturbed in the Yakutat bog, hidden from standard shipping lanes and aerial patrols, in a small valley that experienced perhaps 6 days of clear visibility per month amid the perpetual Aleutian fog. Japanese carrier forces had already retreated west after the catastrophic Midway defeat. The young pilot's death became another statistic in a war increasingly unfavorable to Japan. Then, on July 10, 1942, an American PBY Catalina, piloted by Lieutenant William Thies, became lost. Navigation in the Aleutians was treacherous, magnetic compasses unreliable, landmarks obscured by near-constant fog. Thies had been navigating by dead reckoning when he glimpsed the Shumagon Islands through a break in the clouds. Recognizing his location, he corrected course for Dutch Harbor, electing to fly directly over Akutan Island to save time and fuel. Machinist mate Albert Knack, serving as plane captain, happened to glance down at just the right moment. Through a fleeting gap in the fog, he spotted an unusual shape in the marsh below, something that did not belong. The bright red circles on the wings were unmistakable. Thies circled the site multiple times, carefully noting the coordinates. The Zero appeared remarkably intact. A prize beyond imagination, he immediately returned to Dutch Harbor to report the find. Within hours, a recovery team landed near the crash site. What they found surpassed expectations. The Zero had landed in perhaps the only spot on Akutan Island where the bog was soft enough to cushion the crash, yet firm enough to prevent sinking. The marsh acted as a natural shock absorber, dissipating forces that would have shattered the airframe on solid ground. Aside from a crushed windshield, bent propeller tips, broken landing gear, and damaged wingtips, the aircraft remained largely intact. The recovery team removed Koga's body and buried him with military honors on a hillside overlooking the crash site. They noted the extensive medical taping, suggesting previous injuries or preventative measures against high-G maneuvers. His personal effects, including his pistol and sword, were recovered for intelligence purposes. Then began the arduous task of extracting the fighter from the Aleutian bog. The operation required nearly 3 weeks of grueling work, in some of Earth's harshest conditions. Workers built a makeshift road of logs and planks, slowly winching the captured fighter across half a mile of treacherous terrain to Broad Bay for barge transport. The operation proceeded in relentless damp cold, with equipment freezing or rusting overnight, yet the prize justified the effort. By late July, the Zero was loaded aboard a cargo ship for transport to the United States. The vessel carrying history's most important captured aircraft departed the Aleutians in early August, sailing south through waters recently contested by Japanese and American fleets. The Zero arrived in Seattle on August 1, 1942, and was immediately transferred to a barge bound for Naval Air Station, North Island near San Diego. The aircraft reached San Diego in mid-August, where it was unloaded under heavy guard and moved to a secure hangar. 24-hour military police protection ensured no souvenir hunters could damage the invaluable prize. Word of the capture spread through Navy aviation circles with electric excitement. For the first time since the Zero's devastating debut at Pearl Harbor, American engineers and pilots would have the opportunity to examine the legendary fighter in detail. Navy Captain William Leonard, who would later command a carrier division in the Pacific, collected a treasure that unlocked so many secrets at a time when the need was so great. Marine Lieutenant Colonel Kenneth Walsh, who would survive the war as an ace with 21 kills, would later state, that knowing what to do with a Zero on his tail, information that came directly from studying Koga's aircraft, saved his life several times. The race was on to restore the Zero to flying condition as quickly as possible. Every day the aircraft remained grounded was another day American pilots faced an enemy they did not fully understand. The restoration team worked around the clock, carefully documenting every detail of the aircraft's construction while simultaneously repairing the crash damage. The work proceeded with astonishing speed, driven by urgency and the recognition that this single aircraft might hold the keys to winning the air war in the Pacific. The restoration revealed immediate insights into Japanese design philosophy. The Zero was built like a precision watch, one engineer noted, with flush rivets throughout the airframe and guns mounted flush with the wing surfaces to minimize drag. Every component was designed for minimum weight and maximum efficiency. The instrument panel displayed remarkable simplicity, with no superfluities to distract the pilot. Just essential gauges arranged for instant readability. Inspection panels could be opened by simply pushing on marked spots with a finger, releasing internal latches. The entire aircraft could be disassembled and reassembled using minimal tools, a crucial advantage for field maintenance on primitive island bases. The team discovered that the Zero weighed between 5,300 and 6,165 kg fully loaded. Depending on ammunition, fuel load, and configuration, roughly 2,000 pounds lighter than the American F4F Wildcat. This extraordinary weight savings came from multiple sources. The Zero lacked armor protection for the pilot, relying instead on superior maneuverability to avoid being hit. The fuel tanks were not self-sealing, trading safety for reduced weight and increased capacity. The airframe itself used minimum structural material, just enough strength for the anticipated loads with no safety margin. The Zero was fundamentally a different design philosophy than American fighters, where American aircraft prioritized pilot protection and structural ruggedness, accepting weight penalties for survivability. The Zero sacrificed protection for performance. It was a fighter designed to win through superior agility rather than absorbing punishment. The captured aircraft revealed other secrets. The engine, a 14-cylinder Nakajima Sakai radial producing approximately 950 horsepower, used a float-type carburetor that would prove significant in combat. The wings folded for carrier storage using a simple manual mechanism requiring no hydraulic systems. The control surfaces were fabric covered over metal frames to minimize weight. Most remarkably, the armament package was formidable for such a lightweight aircraft. Two 7.7mm machine guns firing through the propeller arc and two 20mm cannons mounted in the wings. By September 20th, just 41 days after arriving in San Diego, the Zero was ready to fly. The restoration team had replaced the crushed windscreen, straightened the vertical stabilizer and rudder, repaired the wingtips and flaps, and completely rebuilt the landing gear that had been sheared off in the crash. The original three-blade Sumitomo propeller was carefully dressed and reused. The captured aircraft was repainted. The red Japanese Hinamara rounds covered with American blue circle and white star insignia. It looked like an American aircraft wearing Japanese clothes. Lieutenant Commander Eddie Sanders, selected as chief test pilot for the project, had spent the previous week studying every aspect of the Zero while mechanics completed their restoration. He sat in the cockpit for hours, familiarizing himself with the Japanese instruments, memorizing the control layout, preparing mentally for a flight unlike any he had attempted. Sanders was an experienced test pilot, but he was about to fly an enemy aircraft whose flight characteristics could only be guessed from intelligence reports and combat observations. If those reports were accurate, the Zero was faster, climbed better, and turned tighter than any American fighter. If those reports were wrong, or if the captured aircraft had hidden damage, Sanders might not survive the first flight. On the morning of September 20th, 1942, Sanders climbed into the Zero's cockpit for the first time as pilot, rather than student. Ground crew started the engine, which caught immediately and ran smoothly. The restoration team's work vindicated. Sanders taxied to the runway, conscious that dozens of engineers, intelligence officers, and Navy brass were watching from the tower and flight line. He advanced the throttle, and the Zero accelerated down the runway with surprising eagerness. The lightweight fighter lifted off after a remarkably short ground roll, climbing at a rate that would have been impressive in any American aircraft. For the next hour, Sanders put the Zero through a series of performance tests, carefully exploring its flight envelope. He climbed to altitude, tested stall characteristics, practiced basic maneuvers, and felt out the aircraft's handling qualities. What he discovered in that first flight would change everything. Immediately apparent was the fact that the ailerons froze up at speeds above 200 knots, making rolling maneuvers at those speeds slow and requiring much force on the control stick. Saunders wrote in his report, "The Zero rolled to the left much easier than to the right. The high-speed aileron problem was dramatic and unexpected. At low speeds, the Zero's maneuverability was everything Japanese pilots claimed, capable of turning inside any American fighter with ease. But above 200 knots, roughly 230 mph, the ailerons became increasingly heavy and unresponsive. The fabric-covered control surfaces ballooned with air pressure at high speeds, requiring enormous stick force to overcome. American fighters, with their metal-covered control surfaces and hydraulic boost systems, maintained full control authority at all speeds. Sanders discovered a second critical weakness during negative acceleration maneuvers. When he pushed the stick forward sharply, inducing negative gravitational forces, the Zero's engine coughed and died. The float-type carburetor designed for positive and zero gravity conditions could not maintain fuel flow during sustained negative acceleration. The engine would restart when positive acceleration resumed, but for several seconds, the Zero became a powerless glider. This weakness had profound tactical implications that Sanders recognized immediately. American pilots, being outmaneuvered and unable to escape a pursuing Zero, now had their answer. Sanders noted in his report, "Go into a vertical power dive using negative acceleration if possible to open the range, while the Zero's engine was stopped by the forces involved. At about 200 knots, roll hard right before the Zero pilot could get his sights lined up." Sanders completed 24 test flights over the next 25 days, each one revealing additional details about the Zero's capabilities and limitations. He tested the aircraft at various altitudes, power settings, and combat configurations. He performed mock dogfights against American fighters, with other test pilots flying F6F Wildcats and newer aircraft. The data accumulated from these flights was extraordinary. The Zero's maximum speed was slightly less than the F6F Wildcat, contrary to combat reports suggesting the Japanese fighter was faster. Sanders speculated this might be due to reconstruction weight, as the restoration team had been unable to source exact replacement materials for some components. However, the Zer's exceptional range, over 1,900 statute miles, far exceeded any American carrier fighter. The aircraft could remain airborne for over 6 hours, enabling it to escort bombers deep into enemy territory or patrol vast expanses of ocean. The Zero's rate of climb exceeded American fighters significantly, capable of reaching 20,000 ft faster than an F4F could reach 15,000 ft. In turning combat at low speeds, the Zero could complete a full circle in time for American fighters to complete only 3/4 of a turn. These performance characteristics explained why early war combat had favored Japanese pilots. So, decisively, at low speeds and in turning fights, the Zero was simply superior to anything America fielded in late 1941 and early 1942. But Sanders' tests revealed that these advantages came with exploitable weaknesses. The Zero's light construction meant it could not withstand battle damage. Hits that would merely damage an American fighter often proved fatal to the Zero. which lacked armor and self-sealing fuel tanks. The right field materials analysis of captured Zero components revealed aluminum alloys of excellent quality, but used in thicknesses American designers would consider inadequate. The Zero was built to minimum tolerance with no safety margins for combat damage. Sanders' final report synthesized all the test data into actionable intelligence. American pilots should avoid slow-speed turning fights, where the Zero's maneuverability dominated. Instead, they should use diving attacks utilizing the superior high-speed characteristics of American fighters. When a Zero pursued, American pilots should enter a steep dive, preferably with negative acceleration to kill the Zero's engine, then execute a hard right roll at high speed where the Zero could not follow. American fighters should use their superior armor and firepower to absorb hits while delivering devastating bursts that would destroy the fragile Zero. Team tactics should replace individual dogfighting with wingmen covering each other and using coordinated attacks to negate the Zero's turning advantage. These recommendations were compiled and distributed throughout the fleet with unprecedented speed. Pilots preparing for combat received detailed briefings on the Zero's characteristics and how to exploit its weaknesses. The information was incorporated into training programs, with instructors teaching the high-speed dive and hard right roll technique to every new pilot. Combat veterans who had survived early encounters with Zeros suddenly understood what they had been fighting and how to win. The impact on pilot morale was profound. For 8 months, American naval aviators had faced an aircraft that seemed invincible, capable of outturning and outclimbing anything they flew. Pilots had developed a healthy respect for the Zero that bordered on fear. The official American tactic, when jumped by Zeros, had been simply to run away, a humiliating admission of inferiority. Now, for the first time, American pilots had concrete knowledge of how to fight the Zero and win. The mystique surrounding the Japanese fighter began to crumble. It was still a formidable opponent, but it was no longer invincible. It had weaknesses, and American pilots now knew exactly what those weaknesses were and how to exploit them. But the Aleutian Zero's greatest contribution was not to tactical doctrine. It was to aircraft design, specifically to a fighter that was already under development when Koga crashed in the Aleutians. The Grumman F6F Hellcat would become the weapon that transformed American tactical knowledge into devastating combat results. History of how the Hellcat came to be and how the Aleutian Zero influenced its development would prove as important as Sanders's test flights. The connection between the two aircraft has been subject to historical debate, with some claiming the Hellcat was designed based on the captured Zero, while others note the timeline makes direct influence impossible. The truth lies somewhere between a story of parallel development, timely intelligence, and Grumman's ability to incorporate lessons learned even as their fighter was entering production. January 1942, Grumman Aircraft Engineering Corporation, Bethpage, Long Island, New York. Leroy Grumman sat at his desk reviewing preliminary designs for what would become the F6F Hellcat, and the numbers troubled him. The Navy needed a fighter to replace the F4F Wildcat, something faster and more powerful to counter the reports coming from the Pacific about Japanese air superiority. Grumman's design team, led by Chief Engineers Jake Swerble and Bill Schwendler, had created what was essentially a larger, more powerful Wildcat. The design looked good on paper, but Grumman worried it might not be enough. The early months of 1942 brought increasingly alarming reports from the Pacific. American pilots were being outfought by Japanese Zeros at every encounter. The F4F Wildcat, Grumman's current frontline fighter, was proving inadequate despite being a solid, well-built aircraft. Combat reports indicated the Zero could outclimb, outturn, and outrange the Wildcat in nearly every performance category. Something dramatically better was needed and needed urgently. Grumman's initial F6F designated XF6F1 was planned around the Wright R-26 Cyclone engine producing 1,700 horsepower. This would give the new fighter greater power than the Wildcats, which used the 200 horsepower Pratt & Whitney R1830, though Grumman questioned whether it represented a sufficient improvement. The company had been developing the XF6F1 since mid-1941, with the formal contract signed on June 30, 1941, almost a year before Koga's Zero went down in the Aleutians. Design work progressed rapidly through early 1942, driven by urgent Navy requirements and Grumman's understanding that control of the Pacific War would hinge on air superiority. The Bureau of Aeronautics collaborated closely with Grumman engineers, integrating input from combat pilots returning from Pacific operations. On April 22, 1942, 6 weeks before the Battle of Midway and 7 weeks before Koga's crash, Lieutenant Commander Edward "Butch" O'Hare visited Grumman's Bethpage facility. Fresh from missions in which he single-handedly defended the carrier Lexington against Japanese bombers, earning the Medal of Honor, O'Hare met with engineers to discuss the F4F Wildcat's performance relative to the Zero. His observations were sobering. The Zero was faster than American intelligence had predicted, climbed far better than seemed feasible for its engine, and could outmaneuver the Wildcat with ease. O'Hare stressed that American fighters required more power, superior climb rate, and improved pilot visibility. The day before meeting Grumman engineers, O'Hare had spoken with President Franklin Roosevelt during the Medal of Honor ceremony. The president asked what was needed in a new naval fighter. O'Hare's reply was concise and memorable: a plane that could go upstairs faster. Bureau of Aeronautics Lieutenant Commander A.M. Jackson, working closely with Grumman, directed specific design adjustments based on combat experience. Jackson emphasized raising the cockpit in the fuselage while sloping the forward fuselage toward the engine cowling, providing the pilot excellent forward visibility. His message to Grumman engineers was clear: you cannot hit what you cannot see. These changes were incorporated into the XF6F design before Koga's Zero was even discovered. April 26, 1942, 5 weeks before Koga's final flight. The Bureau of Aeronautics made a pivotal decision shaping the F6F's future. Based on Pacific combat reports and O'Hare's recommendations, the Bureau directed Grumman to fit a more powerful engine in the second XF6F prototype. The original R260 engine was abandoned in favor of the Pratt & Whitney R2800 Double Wasp, an 18-cylinder radial engine producing 2,000 horsepower. This was the same engine used in the Vought F4U Corsair and Republic P-47 Thunderbolt, representing a 50% power increase over the XF6F1. Grumman responded by redesigning and reinforcing the F6F airframe to accommodate the new engine, modifying the engine mount, cooling system, and structural components throughout the aircraft. While the change caused development delays, the performance gains were deemed essential. Grumman projected that the new engine would boost performance by approximately 25% compared with the original design. The decision reflected multiple converging factors. The R2800 had proven reliable in testing, was entering production for other programs, and could be supplied without the delays affecting the R260. Most crucially, combat feedback indicated incremental improvements would not suffice. American fighters required a significant leap in performance to match or surpass the Zero. The first XF6F1T's X1 prototype, still powered by the 1,700 horsepower Cyclone R260, made its maiden flight on June 26, 1942, piloted by Bob Hall. This occurred 8 days before Koga's crash and 6 weeks prior to the Zero's discovery. The prototype handled well, showing no serious flaws, but its engine confirmed Grumman's concern that additional power was necessary. The second prototype, the XF6F3, equipped with the 2,000-horsepower R2800, first flew on July 30, 1942, 20 days after the A6M Zero was found, but 2 months before it would be restored and flight tested. The XF6F3's performance exceeded expectations, with its additional power giving it the climb rate and speed required to compete with the Zero on equal terms. Development did not stop there. Through the summer of 1942, Grumman engineers refined the design using ongoing combat intelligence from the Pacific. When the A6M Zero arrived in San Diego in mid-August, technical analysis began immediately, providing the Bureau of Aeronautics and Grumman with critical data on construction, weight, armament, and design. Though the captured plane had not flown, the intelligence arrived at a pivotal point. The basic F6F design was set, the engine selected, and prototypes airborne. Yet production had not started, allowing relatively easy incorporation of modifications. Grumman engineers examined the Zero with intense scrutiny, searching for ways to ensure the F6F not only matched, but exceeded its capabilities. The Zero weighed 5,300–6,100 pounds fully loaded, while the F6F would exceed 12,000 pounds. This weight penalty required compensation through additional power and smart engineering. Grumman's philosophy differed fundamentally from the Japanese approach. Where the Zero sacrificed protection for agility, the F6F would combine both. Roy Grumman, the company's founder, decided that the F6F could surpass the Zero in most respects without sacrificing pilot armor, self-sealing fuel tanks, or structural durability. The R2800's extra horsepower would offset the weight, shaping every subsequent design decision. The F6F was designed for resilience, able to withstand damage that would destroy a Zero, protecting the pilot with armor behind the seat and a bulletproof windshield. Self-sealing fuel tanks could survive hits without catastrophic fires, and redundant systems with robust construction allowed hard carrier landings and combat resilience. The performance deficit from the extra weight was overcome through raw power and thoughtful design. Data from the A6M Zero, combined with combat reports and Sanders test flights in September and October, guided critical design choices. The F6F's wings were optimized for high-speed performance, with a different airfoil and control layout than the Wildcat. Ailerons were hydraulically assisted and metal-covered, ensuring full control at all speeds, directly addressing the high-speed aileron limitations Sanders noted in the Zero. The F6F's fuel system used a pressure carburetor rather than the float type in the Zero, preventing engine failure under negative G maneuvers. F6F pilots could dive to evade pursuers without engine cutout. Structurally, the aircraft tolerated 9G positive and 6G negative, far beyond the Zero's limits, allowing aggressive maneuvers without risking structural failure. Armament was upgraded to 650 caliber machine guns, compared with the Wildcat's 4. Later versions could mount two 20mm cannons and 4 50 caliber guns, delivering concentrated firepower capable of destroying the lightly built Zero quickly, while the F6F's armored frame could withstand return fire. Raised cockpit positioning improved visibility, addressing Jackson's principle that pilots cannot shoot what they cannot see. The design integrated lessons from defensive tactics, emphasizing situational awareness for mutual support between wingmen. On October 3, 1942, the first production F6F3 flew, just 2 weeks after Sanders' initial tests in the A6M Zero. This timing was deliberate. Production had been postponed to incorporate the latest intelligence. The claim that the F6F was designed entirely based on the A6M Zero is inaccurate. The basic design and engine change predated its discovery. Yet, the captured aircraft allowed Grumman to refine the final configuration and incorporate tactical insights before production. The first production F6F3s reached fleet squadrons in early 1943. Fighting Squadron 9 received its aircraft in February, deploying aboard the carrier Essex for training. Pilots welcomed the F6F enthusiastically. After months in F4F Wildcats facing superior Japanese planes, the Hellcat felt like a major leap in capability. Faster, better climbing, more heavily armed, highly visible, and solid. It was easy to fly, stable, predictable, and forgiving, designed for relatively inexperienced aviators entering wartime service. Carrier landings, the most challenging aspect of naval aviation, were straightforward in the Hellcat. Therabust landing gear absorbed hard impacts that would have collapsed lesser aircraft. The visibility allowed pilots to precisely judge their approach. The controls remained responsive at the low speeds required for carrier approaches. Production ramped up with astonishing speed. Grumman built a new factory at Bethpage specifically for F6F production, with the first aircraft rolling off the line before the factory buildings were even completed. At peak production in 1944, Grumman produced 644 aircraft in a single month, 1 Hellcat per hour, an aircraft production record never equaled. The scale was staggering. Each F6F required approximately 20,000 individual parts sourced from hundreds of subcontractors. The Pratt & Whitney engines were built in 3 separate factories and shipped to Bethpage for installation. Grumman coordinated this industrial symphony with precision that amazed observers. Much of the credit went to Jake Swerble, Grumman's production genius, who organized the workflow and supply chain with unprecedented efficiency. Many Grumman workers had never built aircraft before, yet they produced the most successful carrier fighter of the war. Between the first production flight in October 1942 and the end of the war in November 1945, a span of approximately 37 months, Grumman would produce 12,275 F6F Hellcats from a single factory complex. The F6F made its combat debut on August 31, 1943, 15 months after the Aleutian Zero was discovered and 11 months after Sanders' first test flight. Aircraft from fighting squadrons, 5 and 9 operating from carriers Yorktown and Independence, attacked Marcus Island as part of a carrier raid. The mission was an overwhelming success. No Japanese fighters managed to get airborne, and several were destroyed on the ground. 2 Hellcats were lost to anti-aircraft fire. But in air-to-air combat, the F6F demonstrated immediate superiority. Over the following months, the F6F became the standard fighter on American fleet carriers, gradually replacing the F4F Wildcat on the large carriers, while Wildcats continued serving on smaller escort carriers. By early 1944, the Hellcat equipped 15 carrier fighter squadrons and was rapidly becoming the dominant American naval fighter in the Pacific. The tactical lessons learned from the Aleutian Zero were incorporated into every aspect of F6F operations. Pilots were trained to avoid slow speed-turning fights unless they had significant altitude or numbers advantage. Instead, F6F doctrine emphasized high-speed slashing attacks, diving from altitude to build speed, making a single firing pass, then zooming back to altitude before the more maneuverable Zeros could respond. The Thatchy, developed by Lieutenant Commander John Thatch even before the Zero was captured, became standard defensive doctrine for all F6F squadrons. When jumped by Zeros, F6F pilots flew in mutually supporting pairs, weaving back and forth so that any Zero pursuing one F6F would immediately face head-on fire from the other. The tactic neutralized the Zero's turning advantage by forcing the Japanese pilot to either break off or face a head-on engagement, where the F6F's superior firepower and protection dominated. Pilots were taught to use their speed and power to dictate engagement terms. If the tactical situation favored the F6F, engage; if not, use superior speed to disengage, reposition, and attack from advantage. The F6F's climb rate allowed it to regain altitude quickly after diving attacks, Its speed allowed it to escape from unfavorable situations. Its endurance allowed it to patrol longer and chase fleeing enemies farther than Zeros could follow. November 23, 1943, Gilbert Islands F6F Hellcats from carrier Essex engaged Japanese Zero fighters over Tarawa in what would become the first major test of the new fighter against Japan's best. 30 Zeros rose to intercept the American strike, and the ensuing dogfight raged across the skies over the invasion beaches. When the smoke cleared, American pilots claimed 30 Japanese fighters destroyed for the loss of a single F6F. The Battle of Tarawa demonstrated everything the F6F was designed to accomplish. American pilots, many of them relatively inexperienced, had met veteran Japanese aviators flying Zeros and crushed them utterly. The combination of superior aircraft performance, sound tactics based on knowledge of the Zero's weaknesses, and intensive training had created an unbeatable formula. The battle's outcome sent shockwaves through both American and Japanese commands. For the Americans, it validated the F6F's design and the tactical doctrines developed from studying the Aleutian Zero. For the Japanese, it revealed that American aircraft had caught up to and surpassed the Zero's capabilities. The age of Japanese air superiority was ending, but Tarawa was just the beginning. The F6F would prove its worth in every major engagement across the Pacific for the next 20 months, compiling the most dominant combat record of any American fighter in World War II. June 19, 1944, Philippine Sea, west of the Mariana Islands. F6F Hellcats, from 15 American aircraft carriers, 7 large fleet carriers, and 8 light carriers of Task Force 58 prepared to face the largest Japanese carrier aviation force assembled since the Battle of Midway 2 years earlier. The Japanese had 9 aircraft carriers and sent wave after wave of aircraft to destroy the American invasion. Fleet attacking Saipan. What followed became known as the Great Marianas Turkey Shoot, the Mostone-sided aerial battle in naval history. The first Japanese strike, 69 aircraft, lost 42 planes before reaching the American fleet. The remaining 27 that penetrated to the carriers accomplished nothing while facing a storm of anti-aircraft fire and swarming F6Fs. The second wave, 107 Japanese aircraft, lost 97 before they could even attack. Japanese carrier aviation was being systematically destroyed. Throughout the day, Japanese carriers launched 370 aircraft in multiple strikes. Only 130 returned. The F6F Hellcats, flying combat air patrol over the American fleet and hunting Japanese strike groups, shot down the vast majority. American losses totaled 23 to 30 aircraft, with many pilots rescued from the ocean. The strategic impact was catastrophic for Japan. The carrier air groups painstakingly rebuilt after the losses at Midway were annihilated. The experienced pilots who had trained the current generation were dead. The aircraft that had been hoarded for the decisive battle were gone. Japanese naval aviation would never recover from this single day's losses. The Battle of the Philippine Sea demonstrated the F6F operating at peak effectiveness. The aircraft's exceptional endurance allowed continuous combat air patrols over the fleet. Its climb rate ensured F6Fs could intercept incoming strikes at optimal altitude. Its speed allowed pursuit of fleeing Japanese aircraft. Its firepower and protection meant that in any head-to-head engagement, the F6F held overwhelming advantage. But perhaps most importantly, the F6F's easy handling meant that even relatively inexperienced American pilots could operate the aircraft effectively in combat. By mid-1944, the United States was producing pilots far faster than Japan, and the F6F allowed these new aviators to be thrown into combat with confidence they could survive and succeed. Japanese pilots, by contrast, were receiving increasingly abbreviated training as fuel shortages and instructor losses mounted. By late 1944, Japanese pilots were entering combat with perhaps one-third the flight hours American pilots received. The experience differential, combined with the F6F's technical superiority, created a death spiral for Japanese aviation. Every engagement cost Japan irreplaceable pilots, while American losses were quickly replaced by the training pipeline that was producing thousands of new aviators annually. The F6F's contribution to American victory extended beyond aerial combat. The aircraft was adapted into multiple specialized variants that addressed specific tactical needs. The F6F-3 and F6F-5N fighter variants carried radar equipment in a pod mounted on the starboard wing, allowing them to intercept Japanese night bombing raids. The radar reduced top speed slightly, but night fighter pilots found the capability worth the trade-off. F6F night fighters achieved remarkable success against Japanese night raiders, shooting down bombers that had previously attacked with impunity under cover of darkness. The F6F-3 EPAND, F6F-5P photographic reconnaissance variants replaced guns with cameras conducting crucial reconnaissance missions over enemy territory. Their speed and range allowed them to penetrate deep into Japanese-held areas, photograph targets, and escape before interceptors could respond. Later F6, F5 variants were modified to carry 2,000 lb bombs on a centerline rack and rocket rails under the wings, transforming the fighter into a highly effective fighter-bomber. F6Fs, armed with bombs and rockets, provided devastating close air support for Marine and Army forces fighting across Pacific Islands, attacking Japanese bunkers, artillery positions, and troop concentrations with precision that artillery could not match. By the end of World War II, F6F Hellcat had compiled statistics that remain unmatched by any other American fighter. The aircraft was credited with destroying 5,163 enemy aircraft in Pacific air-to-air combat by United States Navy and Marine Corps pilots, with an additional 60 aircraft destroyed in other theaters, bringing the total to 5,023 when including British Royal Navy Fleet Air Arm victories. Only 270 F6Fs were lost in air-to-air combat, giving the aircraft an overall kill-to-loss ratio of 19:1. Against Japanese Zero specifically, the ratio was 13:1. These numbers reflected the combined impact of superior aircraft performance, sound tactical doctrine derived from studying the Aleutian Zero, and increasingly skilled American pilots facing declining Japanese opposition. The F6F produced more fighter aces than any other Allied aircraft of World War II. Between 305 and 307, Navy Hellcat pilots achieved ace status, with 5 or more victories with slight variations, in counts depending on how shared kills were attributed. The Navy's top ace, Commander David McSell, scored all 34 of his victories flying F6Fs. The Hellcat's combat record was so dominant that late-war Japanese pilots developed what American intelligence called zero fatigue, a recognition that engaging F6Fs was likely to be fatal. Japanese pilots increasingly avoided combat when possible, diving away or fleeing into clouds rather than fighting. This psychological dominance was as important as the technical superiority, as it allowed American carrier groups to operate with near impunity, knowing Japanese air opposition would be minimal and ineffective. The contrast with early war combat was stark. In 1942, American pilots had fled from Zeros whenever possible. By 1945, Japanese pilots were fleeing from Hellcats. The transformation was complete. The Aleutian Zero's role in this transformation cannot be precisely quantified, but its importance is undeniable. The captured aircraft provided the first detailed intelligence on the Zero's capabilities and limitations. Sanders' test flights revealed specific weaknesses that could be exploited tactically. The technical data influenced F6F design decisions at a crucial moment when changes could still be incorporated. Most importantly, the Aleutian Zero destroyed the mystique surrounding the Japanese fighter, proving it was not invincible, but rather an aircraft with specific strengths and specific weaknesses. The combination of the F6F Hellcat and the tactical knowledge gained from the Aleutian Zero or WWII created a synergy that transformed American naval aviation. The F6F was not designed because of the Aleutian Zero, but it was refined based on intelligence from the captured aircraft. The tactics American pilots used were not created by studying the Zero, but they were validated and formalized by Sanders' test flights and subsequent analysis. The result was an integrated system of aircraft, tactics, training, and industrial production that overwhelmed Japanese aviation. By war's end, Japan had produced approximately 10,500 Zeros, their primary fighter throughout the conflict. The United States produced 12,275 F6F Hellcats in 37 months, plus thousands of F4U Corsair and other fighters. The production differential reflected America's industrial might, but the combat differential reflected the F6F's technical superiority and the tactical doctrine that employed it effectively. The Aleutian Zero was destroyed in February 1945, ironically in a training accident rather than combat. While taxiing for takeoff at Naval Air Station North Island, an SB-2C Helldiver dive bomber lost control and crashed into the parked Zero, its propellers slicing the Japanese fighter into pieces. William Leonard salvaged several gauges from the wreckage, donating them to the National Museum of the United States Navy. The Alaska Heritage Museum and Smithsonian National Air and Space Museum also preserved small pieces. The physical aircraft was gone, but its legacy lived on in every F6F that flew combat missions, in every American pilot who knew the Zero's weaknesses, in every tactical manual that incorporated lessons learned from Sanders' test flights. Koga's body, initially buried on Aleutian Island, was exhumed by American Graves Registration Service teams in 1947 and re-earied on Adak Island, further down the Aleutian chain. In 1953, the Adak Cemetery was excavated and 236 bodies, likely including Koga's remains, were returned to Japan for burial. The young pilot, who died at age 19, became an unwitting contributor to Japan's defeat. His perfectly preserved aircraft, revealing secrets that would doom thousands of his countrymen. The historical debate about the Aleutian Zero's importance continues. Some historians argue it was the single most important intelligence capture of the Pacific War, more valuable than coterie or any other source. Others contend that American victory was inevitable regardless, and the Zero's capture merely accelerated trends already underway. Japanese historian and Air Self-Defense Force Lieutenant General Masatake Okumiya, who flew as a staff officer in most major Pacific carrier battles, stated that the acquisition of the Aleutian Zero was no less serious than the Japanese defeat at Midway. The Zero's secrets being revealed to American engineers and test pilots represented a catastrophic intelligence failure whose consequences rippled throughout the remaining war years. Fighter ace William Leonard called the captured Zero a treasure that unlocked so many secrets at a time when the need was so great. Marine ace Kenneth Walsh credited intelligence from Koga's Zero with saving his life several times, the tactical knowledge allowing him to survive early encounters that might otherwise have been fatal. The truth likely incorporates elements of all these perspectives. The Aleutian Zero was not solely responsible for American victory, which rested on industrial capacity, coder breaking, submarine warfare, and numerous other factors. But it was a crucial piece of the puzzle, arriving at exactly the right moment to influence aircraft design decisions and tactical doctrine development. Without the Aleutian Zero, the F6F would still have been an excellent fighter. American industry would still have overwhelmed Japan's production, and American victory would likely have been achieved. But the process might have taken longer, cost more American lives, and involved greater uncertainty about how to defeat the Zero's capabilities. The 19:1 kill ratio reflected the result of multiple factors aligning perfectly. Superior aircraft engineering that balanced both performance and pilot protection. Tactical doctrine developed from careful study of the enemy's strengths and vulnerabilities. Training that prepared aviators for the realities of aerial combat. Industrial production that ensured numerical advantage. And critically, detailed intelligence about the enemy's principal fighter, gained from a single, nearly intact example, recovered by chance in the Aleutian wilderness. Americans, veterans who flew F6F Hellcats during the war, gathered at reunions across the decades after World War II. Many were F6F pilots who had dominated the skies over the Pacific, sharing memories and honoring fallen comrades. Speakers at these events consistently mentioned the A6M Zero and the intelligence it provided. They described how understanding the Zero's weaknesses gave them confidence in combat, how they applied Sanders's high-speed dive and hard right roll techniques, and how the F6F's design incorporated lessons from the captured Japanese aircraft. Veterans emphasized a recurring theme. The Zero had seemed invincible. One former ace explained, "We believed it because we had seen what it could do to our planes in early combat. Then we learned its secrets from the Alaska capture. We discovered it couldn't roll at high speed. Its engine would fail under -G. It was fragile and would ignite if hit. Suddenly, it was no longer invincible. It was just another aircraft, one we could defeat if we flew smart. The F6F gave us the tools. The A6M Zero gave us the knowledge. Together, they gave us victory." The F6F Hellcat remained on the front lines throughout the remainder of World War II, gradually being supplemented by the F4U Corsair as its carrier landing challenges were resolved. After the war, Hellcats were quickly retired from active fleet service, replaced by jets and more modern propeller aircraft. Many were assigned to reserve squadrons, remaining in service into the early 1950s. Others were converted into target drones or scrapped. The last Navy Hellcat retired in 1954, only 9 years after the war ended. This rapid obsolescence highlighted how swiftly aviation technology advanced during and after World War II. A plane cutting edge in 1943 was obsolete by 1954, outclassed by jets flying twice as fast and climbing 3 times as quickly. Yet the Hellcat's combat record ensured it would never be forgotten. Museums across the United States display preserved F6Fs, many restored to flying condition. Spectators at air shows still watch in awe as vintage Hellcats perform, their distinctive sound and silhouette evoking an era when American naval aviation achieved dominance through engineering skill and tactical brilliance. Approximately 70 F6Fs survive in museums and private collections worldwide. 7 remain airworthy, all based in the United States, flown regularly at air shows and commemorative events. Each flight is a reminder of the 12,000 aircraft produced by Grumman, the 34,000 pilots who flew them in combat, and the 5,000 enemy planes they destroyed. The A6M Zero itself survives only in fragments, scattered across museums and in thousands of pages of test reports and intelligence records archived in the National Archives. But its influence on the Pacific War far exceeded its physical presence. A single aircraft, captured by chance, analyzed for a few months, then destroyed, contributed to American victory in ways impossible to quantify, yet impossible to ignore. Lieutenant Commander Eddie Sanders, the test pilot who first flew the A6M Zero, lived to see the F6F's success in combat. He continued serving in aviation test and evaluation roles throughout the war, contributing to multiple aircraft development programs. After the war, he retired from the Navy and worked in the aerospace sector, his expertise invaluable amid rapid post-war technological advances. He passed away in the 1970s, having witnessed the complete evolution of naval aviation from propeller fighters to supersonic jets. Sanders rarely spoke publicly about his role with the A6M Zero. viewing it as simply one assignment among many in a career devoted to naval aviation. Yet those who served alongside him recognized its importance. His meticulous test flights, detailed reports, and analytical observations directly influenced American tactical doctrine and indirectly shaped F6F design. He was a quiet professional who performed exceptionally when it mattered most. The broader lesson of the A6M Zero and F6F Hellcat story transcends World War II. Modern militaries invest billions in intelligence, technical analysis, and threat assessment because the A6M Zero demonstrated how crucial detailed knowledge of enemy capabilities can be. Every captured aircraft, every defector with technical insight, every intelligence source revealing vulnerabilities is potentially another A6M Zero, a key unlocking tactical and technological advantage. Understanding your enemy's limits can determine victory or defeat. A single piece of hardware, properly analyzed and exploited, can influence weapon system design, tactical development, and the outcome of battles. The A6M Zero arrived precisely when it could affect F6F development. Sanders's test flights exposed weaknesses at the moment pilots needed confidence to face the Zero. Tactical lessons were distributed when training programs could incorporate them. A year earlier or later, the impact might have been minimal. Timing was perfect, and America leveraged it fully. The Zero in 1942 was arguably the world's top carrier fighter, outperforming anything the U.S. fielded in many respects. But America's ability to mass-produce thousands of F6Fs, train tens of thousands of pilots, and sustain prolonged combat across an ocean gave it advantages the Zero's technical excellence could not overcome. Quality matters, but quantity has its own quality, especially when combined with tactical intelligence and sound doctrine. The F6F Hellcat and the A6M Zero represent two sides of the same equation. The Hellcat was the product of American industrial might, engineering skill, and tactical intelligence synthesis. The A6M Zero was fortune's gift to American intelligence, a stroke of luck revealing critical enemy information. Together, they created an unbeatable combination, transforming U.S. naval aviation from defensive weakness in early 1942 to overwhelming dominance by mid-1944. The young Japanese pilot who perished in the Aleutian bog could not have known that his preserved fighter would contribute to his nation's defeat. His wingman, hoping he survived, could not have foreseen that sparing the aircraft would doom thousands of their comrades. The American salvage crews struggling in that Alaskan marsh could not have realized they were recovering the key to Pacific air superiority. Eddie Sanders, taxiing the captured Zero for its first American flight, could not have fully grasped that his tests would influence a fighter that helped win the war. History is shaped by such moments, when chance and preparation intersect, when opportunity meets skill, when a single piece of intelligence arrives at exactly the right time to change events far beyond its apparent significance. The A6M Zero was such a moment, and the F6F Hellcat its legacy. One captured plane, one skilled test pilot, one moment when intelligence, design, and tactical doctrine converged to create a weapon achieving a 19.1 kill ratio, sweeping Japanese aviation from the Pacific skies. The transformation of American naval aviation from underdog to dominant power resulted from the convergence of industrial capacity, engineering excellence, skilled pilots, and intelligence. The A6M Zero revealed that the seemingly invincible Japanese fighter had exploitable flaws. The F6F Hellcat was designed and employed to exploit those flaws mercilessly. When American pilots flew F6Fs in combat, they carried not just superior technology, but superior understanding. They knew the Zero's weaknesses because Sanders had uncovered them. They knew how to exploit those weaknesses because tactical doctrine had been rewritten based on his flights. They knew victory was possible because the myth of Japanese invincibility had been shattered by hard intelligence from a captured aircraft. The 19.1 kill ratio was inevitable. a testament to what occurs when opportunity meets skill and intelligence. The story of how one test pilot's captured Zero transformed the F6F Hellcat into a 19-to-1 killing machine shows that warfare is decided not only by courage and firepower, but by intelligence, adaptation, and learning from the enemy. The F6F Hellcat and the Aleutian Zero together wrote a chapter in aviation history that still resonates 8 decades later, proving that sometimes the greatest victories come not from destruction, but from understanding.